My name is Alessio, I'm from Italy, and I'm a sales manager of AMX Automatrix. Just a few words about our company before to start to talk about pressure sintering, that is our application field. AMX Automatrix is an Italian company. We are located here in the north part of Italy. And everything happens here, starting from the basic R&D. We have our application lab inside, the mechanical designing, and we also have an internal software house. We are an Italian enterprise, but we deal worldwide. Our major customers are obviously located in Asia, the 70% of the business in Asia, but also Europe and also East Europe is actually growing very fast. We have a 70% of the business that is Asia, as I was mentioning before, including Singapore, Malaysia, Japan, China for sure, South Korea and Taiwan, Germany for sure, and other equipment across Europe, and now also the United States is growing with this technology. So, let's talk a little bit about our application and how pressure sinter can be useful for the next generation of the vehicles. The reason why we are here today, you can be a battery designer, you can be a powertrain inverter designer, or you can be related to some other business of car making, but anyhow, basically is to boost the performance of the circuit. Power density is nowadays target for everybody, so boost the performance of the circuit, squeeze the performance of the circuit, but at the same time to reduce the dimension. Because a lower dimension has two main benefits. First of all, obviously, the circuit will be lighter, but the second will be also cheaper. Several factors and several fields can be interested to our technology, but for sure automotive is the next most important business for the next 4 or 5 years. We can talk about power electronics in different area of the car. We can talk about the door area, servo motor, lighting, active and passive safety, as you discussed before. The colleague of Porsche and the colleague of Conti talk a little bit about this topic, but our focus is mainly the main powertrain inverter. This is the most crucial area for our application. Typically, from our observation, let's say, point, we are seeing 3 most important trends in terms of architecture. These are the typical 3 kind of architecture that we are seeing worldwide. The first one, historically, is the one on the center, invented by Infineon some years ago. That is the classical main powertrain inverter composed by 3 half-bridge packages, the one that you can see in the center, to create the 3 phase, let's say. Then we have the now popular modular switching package solution, that is the one on the left side, and the one on the right side that is also pretty old technology that invented by Toyota and Denso Group 15, almost 20 years ago. Please note that this is not just a theoretical example. These are applications that are actually running every day on our street. On the left side you can see the worldwide, let's say, most famous inverter, that is the actually Tesla Model 3 inverter. We have some example of half-bridge packages that are very diffused, and on the right side the double-side cooling format applied by Denso in this case. As I was mentioning before, this is not just theory, but we already have a lot of vehicles in the street running with this kind of inverters. So, just a last marketing slide before to dive in the pressure sintering. Some weeks ago, some month ago, when I used to have this presentation, I used to say that this business is really growing. Roughly, we were talking about a plus 24-25% year after year. This is the trend of the silicon carbide, and this is also the trend of the substrate and the vehicles. As you can see, these 3 topics are strictly related. It was wrong. It's definitely higher. After COVID-19, all the people is looking in a direction of electrical vehicle, and so this business and this market is really booming. I don't know how many of you today are driving an electric car. How many? How many of you have an electric car? 1, 2? Okay. But probably if I will ask, how many of you in 2028 are thinking about the idea to drive an electric car? I'm sure that it will be much more higher. So is an interesting, marketing analysis, but it means that we have a lot left to do in the next years. Okay, what is pressure sintering? Pressure sintering is basically a heat treatment that consists in applying, obviously, temperature and pressure at the same time to a powder component. Can be silver, typically, or can be also copper. Which are the benefits? The benefit is that we can have a reliability of the joint just adding 200-250 degrees Celsius of the process, but the melting point will be much more higher. Roughly, we are in front of a piece of metal that will melt around 900 degrees Celsius. So you can really boost the performance of the circuit without any risk of the bonding. What else? Thanks to this technology, you can have a best thermal conductivity, and also you will have a lower electrical resistivity. In addition to this, we have some data and some analysis from Fraunhofer Institute that show that also in terms of mechanical joint, this technique gives to the component a higher lifetime because there is a certain inductivity at micro scale, and so we have some study, as I was mentioning before, that show that this technology can reach more than 100 times the standard lifetime of a standard reflow interconnection. Here we have a short video. Let me see if I can put it in the video. Okay, anyhow, of a diffusion of two, in this case was gold particles. Anyhow, we are talking about nano or microparticles typically. Here you can see the difference between a pressure sintered layer, the one on the top, and a standard reflow interconnection that is the one on the corner. Please note that the two scales are different, but what is interesting in my opinion for you is to observe the difference between the black dots and the white dots. As you can see, the porosity in the first image is less than 10%, in front of a standard reflow interconnection that has a porosity that is in the range of 20-25%. Due to this, there are several physical differences in terms of electrical conductivity and thermal conductivity, as I was mentioning before. Obviously, when you talk about pressure sintering, it is also important to focus the attention on the material. As I was mentioning before, typically in mass production worldwide, at the moment there are only, let's say, silver sintering application, but copper will be probably the next stage. Why? Because in terms of physical property, the two materials can have a similar behavior, and at the same time there are some expectations in terms of saving. Here we have the classic, let's say, production workflow scenario. So obviously you choose the material based on the metallization of the substrate and the backside metallization of your die, silicon or silicon carbide. You apply the material using stencil printing, nozzle dispensing, any kind of method. Anyhow, you place the paste on top of your substrate. We have a pre-drying process, roughly around 120-130 degrees Celsius. Anyhow, lower than 150, because at 150 the sintering starts. After this pre-drying of the material, you place the die, as I was mentioning, IGBT of silicon, Diodes, Mosfet, but also passive component like a gate resistor and NTC. And then it's time for pressure sintering, characterization of the circuit, electrical testing and so on, wire bonding and molding. This is the typical workflow scenario. Just a few words about which are the concrete application of this new bonding method. First of all, you can work with pressure sintering at die level. So as you can see in this case, you can see what we call typically advanced package. So we have dies, we have maybe a passive component like an NTC in this case, and then on top of the die clips like in this case, or copper foil and so on. All these kind of elements can be pressure sintered. All these components can be pressure sintered. This is a first possible application. Honestly speaking, it's the most diffused, but we are already in mass production also with this kind of architecture, the one that I was showing to you before. So the DSC package. DSC also noted as a 3D package, consists in create a 3D architecture of the power package, mounting the diodes first, then we will have spacers, and finally a second DBC on top to dissipate the heat. This is pretty interesting because it gives to the package the possibility to have a higher thermal conductivity from both sides. So this is also an interesting application field. It consists, as I was mentioning before, in 3 layers, pressure sintered, but also in this case we are in mass production with some customers. Third possible application case is what is typically called second level of sintering. So to take the package after the molding and go to mount using a pressure sintering method between the already molded component on top of an SiC. Obviously in this case, what it is important is the thermal dissipation. Obviously we are not talking about electric. I just want to close my presentation showing one slide that the professor yesterday evening was asking, that is related to characterization. So I had this slide this morning. Why it is important to talk about characterization? Because moving from standard electronics to power electronics, the criteria are completely different. The reliability is a must in power electronics, and expected lifetime is much more higher. And obviously also the failure rate must be slower. If a laptop can fail, I do not expect that my car after 3 years will fail. And here we have a collection of what are the typical investigation criteria. I cannot comment a lot about this because typically the investigation criteria are very confidential in the automotive industry and in the semiconductor industry because reveal a lot of failure analysis, yield, and so on. So our customers typically are not so open to disclosure about this. But here you can see some of the most diffuse analysis that we see after the pressure sintering. So die share, so check which is the pressure that the component and the bonding will survive. Check the thermal conductivity by laser flash, which is also another interesting method. Temperature cycling and temperature shocks. These are the most, how can I say, interesting analysis criteria. We have our lab in Italy. So we are welcome in Italy anytime if you want to test this new technology, professor obviously. And our partner for the area here in Romania is ICCO. So in case of any question, you have my email here, but you can also refer to ICCO. This is what we do. We have a full series of sinter press. So actually our business is 100% sinter press because it's really booming. But at the same time, we are enlarging our gamma, inserting some new equipment in the direction of front end for silicon carbide, but also analysis. We are now developing an acoustic microscope that will be ready in a few weeks. That's it from my side. I don't know if you have time for a conclusion. Anyhow, the market trend of pressure sintering and more in general about silicon carbide is definitely booming. We have seen some of the most interesting architectures in terms of inverters. We talk a little bit about what is pressure sintering, and if you are interested to know more about this method, please feel free to